Appendix Measuring Real GDP. This appendix explains the method used by the Bureau of Economic Analysis, that is BEA, to calculate real GDP using a measure called chain dollar real GDP. We begin by explaining the problem that arises from using the prices of the base year and how the problem can be overcome. The problem with base year practices, also known as Lasperer's index. Macroeconomists entertain two related measures of GDP. One is nominal GDP, which is the total money value of goods and services produced in an economy in a given period, say a year, and real GDP, which is the total quantity of these same goods and services. Since goods and services are qualitatively different, economists cannot sum their quantities in their natural units. Like try adding 10 pounds of tomatoes to 2 laptops to 5 financial services. While each commodity bundle has its own quantity, these quantities are incommensurable. To overcome this problem, nominal GDP is readily calculated in money terms by multiplying quantity produced with its price. This gives a common standard of measurement. Over time, nominal GDP can grow or contract for two reasons. Because quantities change through greater or lesser production. Second, because price change via inflation or deflation. And here, say the macroeconomists, lies the solution. If we purge nominal GDP from the effect of inflation and deflation, we end up with real GDP. This purging is technically straightforward. Instead of multiplying each commodity by its current money price PI, which changes from year to year, we multiply it by the price PII prevailing in a particular base year PBI. In this calculation, prices are always the same by definition. And since the only thing that changes now are the quantities being produced, we end up real GDP denominated in the base year prices. But in this method arises the problem of growth of real GDP, which is highly sensitive to the choice of base year. To illustrate, consider a hypothetical economy that produces only two commodities, 1000 pounds of tomatoes and 2 laptops. Next, let's choose 1990 as our base year and assume that tomatoes in that year cost $2 per pound while a laptop costs $2,000. In this case, real GDP denominated in 1990 dollars would be $6,000, that is 1000 times $2 plus 2 times $2,000. Now skip to 1991 and imagine that in that year the economy grows by producing one additional laptop. This increase means that real GDP in 1991 denominated in 1990 prices is $8,000. That is 1000 into $2 plus 3 into $2,000. Comparing to 1990, real GDP grew by 33.3%. Now, instead of using 1990 as our base year, let's use 1991. Production level remain unchanged. 1000 tomatoes and 2 laptops in 1990 and 1000 tomatoes and 3 laptops in 1991. Base year prices, though, are no longer the same. In 1991, our newly chosen base year, tomato prices doubled to $4 per pound, while laptop prices are halved to $1,000. Under these new conditions, real GDP for 1990, this time denominated in 1991 dollars, is $6,000. It is 1000 into $4 plus 2 times $1,000. While real GDP for 1991, also in 1991 dollars, is $7,000. That is 1000 into $4 plus 3 times $1,000. In this example, real growth is only 17%. So here I have calculated the real GDP in 1990 prices on the top and the real GDP of 1991 in 1990 as base year. So you can see the real GDP in 1991 is 33.3%. Where after changing the base year from 1990 to 1991, so here we are calculating the real GDP in 1990 in 1991 prices and the real GDP of 1991 in 1991 prices or base year. So here you can see the real GDP has increased only by 17%. This differences in change in real GDP after changing base year is because the prices are not same in both. Though the production is the same, the prices are have changed from one year to another year. This will give a different measure of real GDP when we change base or calculate the production from the different prices. And this is the simplest of example, one in which the production of laptop is rising and tomatoes is falling, might yield positive real GDP growth with one base year and negative real GDP growth with another. So the real GDP in 1991 at 1990 prices is 33.3%. Real GDP in 1991 at 1991 prices is 17%. So we get a different number for the percentage increase in production. In other words, real GDP is affected not only by the actual quantities being produced but also by our choice of base year. And since there are numerous base years to choose from, the same real GDP can end up having many different magnitudes. The base year problem logically means that there is an uncertainty in real GDP because relative commodity prices change from year to year. So in the example we saw that the prices of tomatoes has increased in 1991 from $2 to $4, and the prices of laptop has decreased in 1991 compared to 1990. So each base year will generate a different measure of real GDP, and since there is no way to determine which base year measure is correct, the choice is always arbitrary. This arbitrariness leaves us with inherent and irreducible measurement uncertainty. Chain dollar real GDP, also known as Fisher Index or value production in the price of adjacent years. To overcome this base year problem, economists devised a fix rather than using a single base year. They chained together many adjacent base years. This is a bit like a moving average. They calculate the growth of real GDP between consecutive years, using the first year in each pair as the base, and then chain together resulting growth measures to calculate real GDP levels. This method claims to fix or at least lessen the base year problem. This method has 3 steps: value production in the price of adjacent years, find the average of 2% changes, link or chain to the base year. First step, value production in adjacent year at the prices of both years. Part A shows the nominal GDP calculation for 2012, that is the quantity produced of 2012 valued at the price of 2012, which is $145 million. Part B shows the nominal GDP calculation for 2013. The quantity produced in 2013 valued at the price of 2013, which is $172 million. Part C shows the value of the quantities produced in 2013 at the prices of 2012, which is $160 million. Part D shows the value of the quantities produced in 2012 at the prices of 2013, which is $158 million. Second step, find the average of 2% changes. So value of production in adjacent year, that is 2012 production at 2012 prices, 2013 production at 2012 prices. So the percentage change in production at 2012 price is 10.3. In the same way, 2012 production at 2013 prices and calculating 2013 production at 2013 prices. So the percentage change in production at 2013 price is 8.9. The average of the 2% changes in production is 9.6. Third method is link or chain to the base year. To link to the base year, we repeat the calculation to obtain the real GDP growth rate each year. Real GDP equals nominal GDP in the base year, which currently is 2009. By applying the calculated growth rates to each successive year, we can obtain chain dollar real GDP in 2009 dollars. In the figure shows an example with real GDP equal to nominal GDP at $75 million in the base year, 2009 and assumed growth rates of real GDP for each year between 2006 and 2013. The 2013 growth rate is 9.6% that we calculated earlier. Starting with real GDP in the base year, we apply the calculated percentage change of 2007%. So real GDP in 2010 was 2.7% higher than $75 million, which is $77 million. Repeating the calculation, real GDP in 2011 is 3.5% higher, which is $80 million, and in 2012 real GDP is 4.6% higher, which is $83 million. In 2013, real GDP is 9.6% higher than $83 million, which is $91 million. The same method is used to chain link the years before the base year. For example, real GDP in 2008 is 8.2% lower than in 2009 at $69 million.